Hello, everybody, and welcome back to SciByte. And until we get a more clever tagline, that's all the introduction you get. My name is Jeremy, and joining me on the Skype line on every episode is Heather.
Hi, guys.
Now, this week, we're going to be talking about dark matter and dark energy and why the dark matters.
Interobligatory pun.
Of course. I just had to get it out of the way.
There you
now,
go.
Dark matter and dark energy are actually fairly recent things in science, and really a lot of mystery involving the details of both of these. So a lot of this week's episode is going to be a little bit theoretical, but I promised last week that it wouldn't be all just talking out our butt about things that we don't really understand. We'd actually have some technology. But first, I want to talk about one of the dudes with the coolest name in all of science. Get this, Fritz Zwicky. Tell me about this dude, Heather.
This dude is the first person that provided evidence with the presence of dark matter. This guy wouldn't just sit on his laurels just doing that. He has a whole stretch of other things. He discovered 120 supernovae.
And I think we're going to be talking a little bit about some of those supernovas later on and how they pertain to some of the studies around dark matter.
Yes. Yeah. Now what he did is he took math, the virial theorem. This is a lot of math that says that for a spherical distribution of a massive object, stars, like a galaxy, that the total kinetic energy, that's the moving energy of the object, has to equal -1.5 times total gravitational potential energy. That's like, potential energy is like that resting energy, you know, when you have something sitting on a table.
Sure, that makes perfect sense. I mean, if you take the math and you just run it through a meat grinder, I don't understand any of that.
That's okay.
But basically, this viral theorem is what pointed to the fact that dark matter should be present in the universe.
Yes,
because of this imbalance, because his math said it should be one way, and we saw that it looked like another way.
Yep.
Now,
so there had to be something else there to balance out.
Right. And another, one of the ways that I had heard that scientists first started thinking about the idea of dark matter is because of galaxies. They looked out into the universe, and it was actually a kind of on accident, as I understand it, and you can correct me along the way if this story that I tell is wrong.
Okay.
But there was a group of scientists looking at the rotational spin of galaxies that we could see straight on. And they found that the stars on the outer rims of those galaxies were actually spinning at very nearly the same rotation speed as the stars closer to the center of that same galaxy.
That is correct.
Under Einstein's theories of gravity and Newton's theories of gravity, this just doesn't work. Something closer to a massive object like the supermassive black hole that's supposed to be, it would be spinning much faster. But in the case of galaxies, they're all spinning at the same speed.
Yeah, so you get left with one of two things. One, none of our physics works on the galactic scale. Or two, there's a lot more mass there somewhere that we just can't see.
So modern scientists decided to take the latter route. Now, I can kind of understand them not wanting to debunk Einstein and Newton. I understand that. But if you're taking a look at something that's a model like that, and you already know it doesn't work, like we just covered on our gravity episode 2 weeks back, that Einstein's theories don't work at a quantum level. Newton's theories don't work even at a molecular level, if I remember correctly. They break down at different scale levels. Now, isn't it possible, though, that one or both of those models is just not fit to measure galaxies?
Oh, it's certainly possible. Now, a lot of scientists will take a first route saying, assuming that the physics we know as actual physics and it follows the rules we think it should, then we need this to happen. We need there to be more mass in these locations in order for all of the stars we see and the gas we see to follow the rules that we have laid out. Now, we may run into a point where we say, no, these rules don't really work. But until we get a better idea of how everything interacts, and how it interacts on the large scale and the atomic scale, and if you can have one set of rules for all of that, then we just that's really
what a lot of scientists are looking for right now, at least physicists.
Yes.
Unification theories. I mean, maybe I'm just being a little bullheaded here, but it does seem at least slightly as if it's kind of one of those situations where to a man with a hammer, every problem looks like a nail. You know, they had this problem with galaxies not flying themselves apart, basically, and they just decided, well, there's stuff we can't see. I mean, I know that seems like a really simplified version of it, but let me take a different route on this because, and I forgot to mention to you this before the show, so I apologize for throwing this in your face, but I actually read a book.
Oh.
I know. Try to hold yourself together. I read a book called Through a Universe Darkly, and it was written several years ago, and they probably know more about dark matter than they know now. But it was basically a history lesson on how the whole concept came to be.
Okay.
Not a very good book, I'll be honest. I don't recommend it as highly recommendable reading, but the first half of the book, maybe even more than that, was actually talking about the concept of what scientists used to call the ether, which was basically, we can't see it, so we just make something up.
Okay.
All of this talk about dark matter kind of leads me back to thinking about that. And so maybe you can help me here. There's got to be some sort of evidence, some sort of math or proof or something that really, maybe not concrete, but mud. Can we get some mud going on here?
Mud going on.
Can we get something that's close enough for science?
Close enough for science.
Tell me what dark matter does, and how can we see its effects?
All right. So, here recently in the last year, there was an undergraduate student in Australia that, said this dark matter they think would be low in density, high comparatively in temperature. So they took
compared
X-rays.
To the rest of the universe around it, or what?
Yeah, compared to the empty universe. So they went out and they looked and they said we think it would come out in the X-ray. So they went and they took. She was part of a study that took a few months to look over wide regions of the sky to look for this X-ray specifically, and they actually found some.
They actually discovered evidence of dark matter using X-rays?
Yes, using this. It was the same that they theorized would be out there. So it's the first tangible evidence. Now, of course, it could always be something else. There could be another reason behind it.
There are more things in heaven and earth.
Horatio.
Right.
Indeed. Especially in the universe.
Right.
It's the first tangible evidence that we've seen of something out there that could prove this dark matter theory.
Now, when you talk about X-rays, isn't that, if I understand correctly, isn't that also what is defines the cosmic background radiation?
No, that's actually cosmic microwave radiation.
Oh.
Microwave.
That's like the exact opposite, isn't it?
Not the exact opposite.
I was close, right?
But you were... Enough for science? I don't know.
No, but what I was getting at here is that I was going to ask, is this X-ray study that you're talking about, is it the same one that used the cosmic background radiation to kind of look for cold spots, I guess you might call them? Places where the radiation varies enough to actually be taken as some sort of, maybe not evidence, but indication that there may be dark matter present out in these certain regions of space.
It's a different satellite. I think the one you're speaking of is the Wilkinson Microwave Anisotropy Probe. That is a tongue twister.
So that's the one that that was using the cosmic background radiation as kind of a point of reference in a sense.
That was looking. The cosmic background radiation is about 380,000 years, roughly or so, after the Big Bang. So they go out and they look and they measure temperature. Now it's kind of anisotropy means that it's sort of polarized, so you can only see it if you look at it from certain directions. So they reference the temperatures at different points in the sky in order to see the temperature variations to within a millionth of a degree.
Whoa, a millionth of 1 degree. Yes. Fahrenheit or Celsius?
Celsius.
That doesn't matter. It's 1 millionth.
It's 1 millionth. It's really small. So it's not like.
When was this probe or is it still out there?
It was launched in 2001, and I believe it was extended because it was doing a lot of good research. They tried to extend it.
Oh, I think you mentioned this one to me once before. Is this the one that's out on the other side of the moon so it doesn't get interfered with the Earth's heat and stuff like that?
Yes.
The Lagrange point?
Yes, the Lagrange point too. So it's out past the moon, so the measurements that they're taking are not interfered with by the sun, the Earth, the moon. It's got a little heat shield to protect it from whatever else it can, so that it can kind of help block all of that all at once, so that it can get a lot more into the millionth of a degree, increase its accuracy.
Well, that's probably why it can be so accurate, is because it doesn't have to worry about ape interference.
Yes.
That's us, by the way. So what have they, so far, you've got a whole list of, this is a whole bunch of numbers. I'll just let you tell me. Yeah. What have they found out so far using the Wilkins Anisotropy Microwave Probe?
Well, they're able to take a census of the universe. And from this temperature, they can kind of see infer gravitation, and from that infer matter. So they can kind of look and see at different points and estimate how much atoms, what percentage of atoms there were in the universe. What, we talked about an episode or two ago, how atoms nowadays only make up about, 5% of the universe, and the dark matter and dark energy are pretty much everything else. So it was able to take a census and found that by its standards, dark matter, not made up of atoms, makes up about 23.3% of what they think of the universe.
Wait a minute, did you just say not made up of atoms? What's it made up of then?
Yes. Not atoms. Dark matter. That's the problem.
But it should be clarified that the current theories on dark matter also, it's not antimatter. Those are completely different things.
Yeah, it's different. Antimatter is still matter, sort of. It just has a different spin and like opposite properties.
Whereas dark matter is not matter.
Yeah, it's not matter, but it's interacting with things gravitationally, weakly.
But that's the key, isn't it? It's only gravity. If I understand correctly, dark matter does not interact with the electromagnetic force. It doesn't interact with the strong nuclear force. In fact, anything basically beyond the weak nuclear force, it has no effect on. So that's also why we can't detect it, because we can't see its electromagnetic radiation. We can't see its effect on light waves. They're not affected by dark matter.
We're only seeing how
that is truly invisible.
Yeah, we're only seeing the gravitational. Really, So I spoke a few minutes ago about the study that was showing some X-rays. Mm-hmm. So that may be evidence of us being able to see it more directly. But so far it's just been indirect gravitational forces being affected by something that we can't really see.
So with all this taken in mind, these studies with the X-rays and everything like that, it does seem, this is kind of turning around on what I just said earlier, but it seems like as though science might be actually on the verge of, or on the right track to proving that dark matter is more than just an error in the maths, that it's something, that can be tangibly proven even though we can't see it.
Early evidence, but we're starting to see actual evidence that may prove, to prove it out.
Now that's actually exciting, because I love living in a time where something new is proven. That's always been something that's fascinated me. I've been worried my entire life, I'll be honest, that nothing big would happen in my lifetime and I'd just be stuck here in the same old universe I was born in.
Oh no.
The same one that started with the Big Bang. How do you like that segue, huh?
Nice.
We're going to go all the way back to the Big Bang here, because dark matter and dark energy, even though they both have the word dark in their names, actually don't have a whole lot in common with one another, except that they both affect the same cosmological theory, which is the Big Bang and the whole expansion of the universe and everything like that.
Yes.
Dark matter was introduced to basically solve the problem of galactic formation and being able to stick together and stay galaxies instead of just spinning off willy-nilly. Dark energy. Actually, Heather, maybe you want to introduce what exactly is the problem that dark energy became the solution to?
Sure. Well, we have the Big Bang, and in the first trillionth of a second, trillionth, it expands really fast. And then it slows down and it goes about at a steady rate. Mm-hmm. And then suddenly it starts expanding even faster. Einstein, when he talked about this, called it, the cosmological constant, and came back and said it was his biggest blunder. Turns out maybe not. From Edwin Hubble, he started seeing the expansion rate of the universe. We have the Hubble telescope.
That was way back in 1932. You've got it written here. That is correct. Yeah. So this concept of the expanding universe has been around for quite a while.
Yes. So it's possible that, again, that on really large scales, our theories of gravity and time and space are all off.
Because they don't account for a fact that the universe would continue expanding and actually
expand faster.
Yeah, it's starting to expand faster and faster as time goes on.
Yeah, an accelerated expansion. It's just starting to go really fast. So
science has decided that one of the best answers to this is more invisible stuff. Okay,
more invisible stuff.
I'll save my negativity on this one. I already got that out of my system earlier, but okay. I'll go with it this time. Dark energy. is the answer to the expanding universe and the fact that it's expanding faster and faster.
Yes.
Now, what exactly is dark energy then? How would it cause the universe to continue to expand at a more rapid pace?
Well, it's sort of that's the question. Does empty space have its own energy? Is there something that we can't see that is providing an extra amount of energy? Is it providing a repulsive force? Like anti-gravity?
Have to, wouldn't it? I mean, dark energy would have to be an anti...
Yeah. It's possible that there's just something else there that's transferring energy to the universe and allowing it to expand faster.
Well, that seems even more complicated than dark energy itself. Let's not go there today. So when we're talking about dark energy, it is it very much an idea in its infancy as far as studies that have done anything to prove it. But you did point out one to me that is actively undergoing investigations, and I love the name of this project.
Yep.
It's called Wiggles.
Wiggles.
So we've gone from Fritz Zwicky to Wiggles with a Z.
Yep.
All right, so tell me about the Wiggles Dark Energy Project.
All right, so it's observing how dark energy opposes gravity by speeding the overall expansion of the universe. How dark energy opposes gravity.
But to be clear, calling it anti-gravity is a bit of a misnomer, correct?
Yeah, it's
an opposing force, but it's not an exact opposite.
No, it's not an exact opposite. Now, what they're doing is they're mapping the distribution of galaxies over a huge portion of the universe. And if we remember, the farther away you look, the farther back in time. So you can kind of see how things evolve over time, how they, how things tend to come together. You can check out groups of galaxies farther back in time, groups of galaxies closer in time, kind of see how they interact and kind of compare that. They've made a 3D map of more than 150,000 galaxies to trace the evolution.
That sounds like a really big number, but it's not really all that much of the universe, is it?
No, but it is a lot that we have looked at.
Now, when you say 3D map, does that mean some sort of like a computer model, like a simulation that they can run simulations on this map to kind of see like what that portion of the galaxy may have once looked like when it was closer together?
Yeah, we take what a lot of astronomy does is they take the rules that the physics and what they see, and they input all the data that they can see into big mathematical
supercomputers,
and they spit out, what is this doing? Does it match what we see? Look at it over time. We can go back and look at young spiral galaxies and old spiral galaxies, and we can kind of judge how old they are or young they are by the types of stars in them and where the stars are in their life. So you can kind of plug all of this in there, plug it into a big supercomputer, and it can help map the evolution of these things. And we can.
That's awesome. How long has the Wiggles project been going on? Do you know?
Well, the current batch of data was taken between August 2006 and January 2011.
And that cataloged 150,000 different galaxies.
Yes.
Just in that short amount of time. I'm sure that they continued to do the survey until they've tried to map the entire universe. It's actually a pretty significant chunk just for 4 or 5 years' work.
Yeah, just over 276 nights of data. So
now, if people wanted to keep up to date on more findings through the Wiggle survey, is there like a link or anything? And do they have a website or anything like that?
Yeah, they have a website that has data, and they'll do releases of data every so many years. They'll put out a publication. That'll be in the show notes.
And a 10-minute podcast says the link in our show notes.
Yep, about the Wiggles.
And all about their dark energy survey and mapping the entire universe. That sounds like a lot of fun. Not just the name.
Not just the name.
Well, until I get drafted into the Wiggles program, I think that's all we have time for today. I hope that you guys have enjoyed this episode of SciByte, where we talked all about the dark things that matter. I did it again, didn't I? Now, next week's episode is going to be a complete mystery, just like science itself. We don't actually know exactly what we're going to be talking about next week, so if you have any suggestions, I would encourage you all to leave a comment wherever you're watching this. Also, you can head on over to Jupiter Colony. I don't know if we have a SciByte subforum just yet, But if we don't, you can just put your comments. I'm hoping we do soon. You can just put your comments in the general forum until that time.
Yep.
And I guess that's all. Until next week, everybody, keep your brain buckles on, and we'll see you again on SciByte.
If I try to type the wiggles, it's going to bring the wrong wiggles. I may have doomed us all, too. Science is melting my brain tonight, too.
It'll be fancy.
Okay.
The whole internet will stand and cheer.
Yes.
And wet their pants with glee.